Okay, let's talk about banana orbit. Here's the setup. On the left-hand side plot, we have a torus with a toroidal magnetic field B phi, toroidal magnetic field B theta. R is a major radius. At the center of the cross-section of the torus, we set up a Cartesian coordinate on the x and y, and we can describe the particle guiding center particle motion. So equation of motion for the guiding center on the xy plane using equation 1 and 2. A portion of the motion is along the toroidal magnetic field line. The velocity along the toroidal magnetic field line is b phi b theta over b naught, where b naught is a total magnetic field, and we can project it to x and y axis to have velocity along x and y. We can have a dot where the particle is at, connect that with the origin, assuming that angle is a theta. Then we have we can decompose into x and y. Since this angle is 90 degree, because the velocity is along the b theta, then Vy can be described as this velocity multiplied by cosine theta, where cosine theta can be described as x over r. Then we can describe the velocity along x-axis as such, and y-axis are like in this manner. And on the velocity along y direction has additional term is caused by the vertical drift. The vertical drift is pretty much the sum of the curvature drift and the grad B drift. Basically is a drift due to the magnetic field. We can combine equation 1 and 2, basically divide equation 2 over equation 1 to eliminate dt. Then we ended up getting this equation. We can transform such equation to using the radius dr. So r dr dx equals half dr squared dx, and since r squared equals x squared plus y squared, we can have this, since obviously dx squared over dx is 2x, and then we use chain rule to get the second term. We plug in the dy dx from this. We ended up getting this equation, tidy it up, divided on our small r on both sides. We ended up getting this differential equation describing the particle movement. We can solve this equation with some estimations. We know that v square equals v parallel plus v perpendicular. So the top can be somewhat equal to v square. And v parallel can be described in this manner: v square root epsilon plus x over r, where epsilon is v square minus v naught square over v naught square. It's roughly r, small r over big R. And we multiply dx on both sides and integrate. We get the solution. This is a rather trivial integration is pretty much 1 over square root of x, and we get this equation. We got two solutions, and we can plot it out. I actually have written that into Python script, and it's in the GitHub repository. You can click into that, and it will be in the description as well. The red line is an orbit, and the black line is a perfect circle. Basically, you can imagine the particle is shifted up and down vertically due to this term. So we have up and down two solutions, and then they give us a banana shaped orbit. And we can also estimate the width of the banana orbit by knowing the knowing at x equals r, that's where has the biggest shift. As you can see, is quite trivial because it's monotonically increasing. Then since epsilon is roughly r over a small r over big R, then we can write it in such manner, and then we know that cyclotron length, Lamar radius is that, can be expressed as that, which is pretty much this, similar to this, and we get and then we have b naught over b theta, basically transform this here, and then we have, and then divided small r on both sides, we end up get this. Pretty much the width of delta r, the width of the banana orbit, can be expressed in this way. And the right plot gives us some idea of what it looks like in the real device. The background is a joint European tourist jet, and the plot is pretty much shows the banana orbit. It can be from simply changed to a completely bounce back as if it were in a magnetic bottle. I think this has taken into account of multitude of a factor, and yeah, that's what it's supposed to look like. They will look like a banana like such.